Okie doke, we're going to do one or two example problems dealing with objects that are rolling without slipping. Got to start with the classic, and that is a ball rolling down a ramp. And so we have here a solid sphere, and it's rolling without slipping down an incline. And we are asked to calculate the acceleration of the center mass of the sphere. You might be tempted to look at this and say, oh, it's going down an incline, must be acceleration is g sine theta. Because that would be the case if it were a frictionless block going down an incline, but this is not a frictionless block. It's a sphere that's rolling without slipping, and the analysis is a little bit different. So let's take a look at it. We're going to, since we're looking for the acceleration, it might seem reasonable that we're going to examine forces and torques and things, and in fact we are. So let's start by drawing a free body diagram of the sphere, and I'll draw it down here to have a little bit more room. And let's draw and label the forces acting on the sphere, paying attention to the point of application of each force. Okay, we start with gravity, and as we have done before, even though gravity acts on every different molecule of material in the sphere, we treat it as acting at the center mass, which is in the center of the sphere. So I draw an mg. Oh, by the way, did I specify before that the sphere, this may shock you, has mass m and radius r. There's the old radius r. And we are told also that it is a solid sphere. That can be relevant. Okay, so meanwhile, back to the free body diagram. So its weight is mg. Then we say, what other forces are there? Well, there's clearly a normal force due to the contact between the sphere and the ramp. That acts at the point where the sphere is in contact with the ramp. And it is normal to the ramp, and so it acts through the center of mass, the normal force does, from the point where the sphere is in contact with the ramp. Finally, are there any other forces? And you might think there aren't, but in fact there have to be. And the reason for that is that this thing is rolling without slipping. If there's no friction, then this, even though it's a ball, if you placed a ball in a perfectly frictionless incline, it's going to slide down that ramp. Nothing's going to make it start rolling. And it'll just slide without friction down the ramp when it gets to the bottom, and the analysis would be identical to a frictionless block. But we are told that this thing is rolling without slipping. That means there, in fact, has to be some friction. Because for this to be rolling without slipping and accelerating, going faster and faster, think about this. This object, as the ball rolls down the ramp, it's going to have an angular velocity, which is counterclockwise, as it's rolling. And if it's accelerating down the ramp, the ball's rolling faster and faster, which means it has an angular acceleration, alpha, as it rolls faster and faster. Well, that's not going to happen without an unbalanced torque. And if you look at the free body diagram so far, we have two forces, neither one of which creates a torque about the axis of this ball, about the center of the ball. Because mg acts at the point of application of, it acts at the axis of rotation. And the normal force, even though it is a distance r away from the axis of rotation, which I'll mark temporarily with this r vector, the torque created by the normal force is 0 because the angle between r and the normal force is 180 degrees. So when we say the torque created by the normal force is r n sine phi, phi is 180 degrees, and sine of 180 degrees is 0, and so there is no torque created by the normal force. So there has to be another force, and that force is static friction. Remember that this thing is rolling without slipping. There's no kinetic friction. But if you visualize this thing rolling faster and faster and faster, the reason it's being made to roll is because the bottom is gripping the surface. And instead of sliding, it's gripping. And that the grip opposes the way it would slide. It would slide downhill, and so we have this static friction force, which is acting uphill to prevent it from slipping. And the static friction force also ends up providing the torque required to make this thing rotate faster and faster and faster. So there's our completed free body diagram along with a radius vector r, which is not a force, of course. And so now we're ready to start the analysis. Okie doke. We want to find the acceleration. So I bet we're going to be analyzing forces. This thing is accelerating down the ramp, so its linear acceleration is downhill. Let's use that to designate our positive x and positive y directions. We'll define a coordinate system with positive x pointing downhill in the direction of acceleration. And I can write some net f statements. I will say net f, and the x is equal to, oh, bad mg, you're not in the right direction. So I'm going to plus mg up into components. So I'm going to draw the downhill component mg sine theta and the perpendicular component mg cos theta. And I'll get rid of m because I don't want to have both the force and its components. Okay, so in the x direction, I have mg sine theta minus the static friction force is equal to m times a, and that's the a that we're looking for. By the way, some of you might be tempted to say, oh, friction force, F equals mu times n. You might be tempted to do it, but please don't, because it's wrong. Now, why is it wrong? This is static friction, and static friction is less than or equal to mu times the normal force. It's only equal if you are in a situation where it's just about to slip and you are at the maximum static friction force. We have not been told it's just about to slip. So the static friction is less than mu times n, and so we can't use that as an equality because it's not an equality. So just leave it as that was the inequality was true, by the way, but we're not going to use it. So we just have to leave that as F, S, the static friction force. Okay. That's nice. It has the quantity in it that we're trying to find out, but I don't know what the static friction force is. I have an unknown, so that makes me sad. I need to do something else. I need to generate another equation based on these quantities, and the one I'm going to use is torque. I could do, by the way, net F in the y direction. It's going to tell me that the normal force is equal to mg cosine theta. That's nice. It doesn't help me at all in this problem. So what else do I have left to analyze? I have torques. Net torque equals I alpha. Okay, what is the net torque on this round thing, on this sphere? Well, we've already discussed that the normal force and mg do not create torques. The only force here that creates a torque is the static friction force. So the net torque is equal to the torque created by friction. And the torque created by friction is R times F times sine phi, where phi in this case is the angle between the R vector, which I bet I can't pull. Oh, there it is. The R vector and the static friction vector drawn tail to tail. Uh-oh. Look at that. The static friction vector drawn tail to tail, like so, and that's a 90-degree angle. So phi is 90 degrees, which means sine phi gets arrow 1. And so the torque created by the friction force is R times the friction force. R in this case is big R, which is the radius of the wheel. So that's the torque created by the friction force. That is equal to I alpha. What is I? Oh, I don't know. What is I? Well, I is the rotational inertia, which is 2/5 mr squared for a solid sphere. And where am I? The alpha is alpha. Can I do anything with alpha? Yes. Well, with the equations that we generated on the earlier lesson today, I know that the acceleration of the center mass is equal to alpha times r for an object which is rolling without slipping, which means that for alpha, I can sub in ACM over r. I think I'll do that. So I have RF, which is net torque, equals I alpha, I times alpha, which is ACM over r. Let's see what we have here. RF, I'm just going to rewrite this. RF is equal to 2/5 mr squared ACM over r. Let's do some cancellatory activity. I've got an r squared over r on the right, boom, boom. And then I have an r on each side, boom, boom. And I'm left with the friction force is equal to 2/5 ma. Does that help me at all? Well, yes, it does, because if I look back at the equation I had earlier, you analyzing the force in the x direction, which I'm going to move down here if it's all in one piece. Boom, good. I have mg sine theta minus the static friction force is equal to ma. Well, I know how to sub in mg sine theta minus static friction force 2/5 ma is equal to ma. These are the same a's as each other because they're both the acceleration of the center mass of this ball. Oh, what do we got? M gone, M gone, M gone. And I end up with g sine theta. I'm going to bring the 2/5 a over to the other side is equal to a plus, I just misspelled plus 2/5 a, or 7/5 a. So g sine theta is equal to 7/5 a, so a is equal to 5/7 g sine theta. I am happy.